warahmatullahi wabarakatuh and salam sejahtera. Now we proceed with our subtopic 6.2 Otto cycle. Otto cycle is the ideal cycle for spark ignition engine. Why we call it as a Otto cycle? Because it is named after Nicholas Otto, who built this 4-stroke engine in 1876 in Germany. The piston executes 4 complete strokes within the cylinder. So if you can see here, we have 4 strokes and the stroke called intake stroke, compression stroke, power stroke and exhaust stroke. So in intake stroke, what happens is the air and fuel will enter the cylinder through intake valve, and the piston will moving from TDC to BDC. So, one stroke. The volume inside here, we call it as a displacement volume or maximum volume. Next is the piston will moving from BDC to TDC. This is compression stroke. In the compression stroke, the air and fuel will have a high pressure and high temperature. And this volume is displacement volume. Clearance volume. What happens next is power stroke. The spark plug will ignite the fire to burn the air and fuel inside this cylinder. So, this stroke is power stroke where the piston will moving from TDC to BDC. So, in this process, we call it that the heat addition is in constant volume. And lastly is exhaust stroke, where the exhaust product is expelled through the exhaust valve and the piston will moving from BDC to TDC. So we already have 4 strokes. Okay, next we go to the PV diagram and the schematic diagram of the piston cylinder devices. And if you can see here, we start at the VBDC, which is V maximum, which means we start with the isentropic compression or compression stroke, where the piston is at BDC. V maximum. Okay, so in V maximum, we know that V is the volume is in displacement volume or V maximum. Okay, and then what happened is piston will moving from state 1 to state 2, from BDC to TDC. BDC to TDC, which means it will moving from V maximum to V minimum. And this process is called as a isentropic compression. So next is state 3, state 2 to state 3. In state 3, we call it as a power stroke, where the spark plug will ignite the fire inside this cylinder and the volume is constant. Okay, is in clearance volume. Okay, so here 2 to 3 is in constant volume and there will be Q in here through a spark plug. Okay, and we call it as a power stroke. Okay, next we go to the state 3 to 4. State 3 to 4, which means the piston will moving from TDC to BDC. So from the V minimum to V maximum. Okay, here. Okay, expansion. Okay, it will moving here from 3 to 4, from TDC to BDC, and we call it as a isentropic expansion. Okay, here the combustion product is in this cylinder. Okay, then we will reject the expelled product through constant volume heat rejection, where the piston will moving from TDC, from BDC to TDC. So please concentrate here, because this diagram is quite confusing, then we just follow here. Okay, 1 to 2 is isentropic expansion from V maximum to V minimum. 2 to 3 is constant volume heat addition. Okay, the volume remain as it is in clearance volume. Then power stroke, where the piston is moving from TDC to BDC. Okay, next is exhaust stroke, where the piston is moving from the BDC to the TDC. Okay, so this is an important PV diagram you have to know and you have to remember. Okay, this is a PV diagram and TS diagram of Otto cycle. And as I mentioned before, this is PV diagram. 1 to 2 is isentropic compression. 2 to 3 is constant volume heat addition. 3 to 4 is isentropic expansion, and 4-1 is constant volume heat rejection. And please remember, V1 is equal to V2, V2 is equal to V3. And for the TS diagram, we know that the maximum occurs at state 3, where the process is at the isentropic expansion. Okay, and we can see here that S1 is equal to S2 for isentropic compression, and 3 to 4 is isentropic expansion. And this is comes all the equation. So for Q in here, state 2 to 3, since this is constant volume, therefore we use CV. Okay, CV T3 minus T2. And Q out is also occurs at the constant volume. Therefore, CV T4 minus T1. And the thermal efficiency, the formula the same as the Rankine and Brayton cycle, but in Otto cycle, we don't have turbine or compressor. Therefore, we use W net as a Q in minus Q out over Q in. 1 minus Q out over Q in. Okay, this is the thermal efficiency. Okay, and we can represent thermal efficiency for Otto is 1 minus T1 minus T4 minus T1 over T3 minus T2. Okay, since V2 is equal to V3 and V4 is equal to V1, and we know that V1 over V2 is equal to V4 over V3. This is compression ratio. Then we can replace this with a compression ratio 1 over RV. Okay, 1 over RV. Okay, that's all. Thank you.